ready to marry Courtney Love.
No. So, so yeah, we should have got through the chapter 14 homework by now. It looks like everybody's got that. The chapter 15 homework is due. I can extend the due dates on that if you'd like. I can, I mean, I don't want to push this so hard. I do realize we have other classes and stuff like that, and I don't want to assume I'm the only one, but excuse me. But so if we need to, I can push the quiz off till Wednesday if we'd rather do it like that. Um, because chapter 14 and chapter 15 kind of lay the groundwork for and today we're going to go into chapter 16 and you'll see at least the groundwork for what we're about to start looking into. And so tomorrow's lab will be a little more complicated, I guess. I'm not sure if we need to make it a 2-day lab or if we'll make it the 1 day. I guess, well, we'll see how everybody gets through tomorrow. If it seems, I know the one part of it we'll be able to get through. Basically, it's real similar to what we did last week with just adding up capacitances and things like that, measuring them. Um, with, of course, the added twist of going further, which will be today's chapter and chapter 17 as well. Chapter 17 will kind of bring it through to all the concepts we want to go over with capacitors and the reactances to AC signals. And then after that, we'll be taking a look at inductors. And then eventually we'll do all of them. And that'll be fun. It'll be fun. But so let's see. Yeah, we're after 9 o'clock. So I will start this. We're going to take a look at chapter 16. Oop, let's start there. Chapter 16. And we get some new concepts that we'll be looking at. As you can see here, the topics that will be covered. So what we're looking at is something called reactance. Now remember and keep that in the back of your head, reactance, right? So what the capacitor is going to do, it's going to react to the AC signal. You'll see in this section 16.2 that we have a new term of excessy, and then what it is equal to, and we'll get into what that is exactly. And then looking at series or parallel capacitive reactances, how Ohm's law applies to this, applications, and then taking a look at like the way sine waves charge and discharge current through capacitors, or not through capacitors, if you will. So here's some new stuff. This is so if we as capacitive reactance as a like measurable quantity, it's something that we do look for in AC signal analysis. And here's the classic definition of it, I guess you will. It's the opposition of a capacitor operating at a flow of sinusoidal current. Now, I want you to think along the lines of like resistance, right? Now, resistance was an opposition, excuse me, but you've seen that it was a direct opposition to DC, and then it'll also be the same with AC. But capacitors didn't offer us any like resistive elements in a DC environment. It simply charges up to the full potential of whatever energy source we're applying to it. But now when we get into AC, we get something a little different. So our first symbol here that we see, it's X sub C, okay? And now the C denotes a capacitance. So what the heck is the X? Well, let's take a look at that. You'll notice that the unit of measurement for this thing is ohms, just like a resistor is. And then we have an interesting formula here. So what does X of C equal to as far as AC analysis go? And this is one of those formulas that will follow us through. I won't say, it's up there with Ohm's law, but this one is extremely important for capacitors. In fact, this is the way we actually want to think of capacitors as applied to AC signals. So he has a formula here where he says X of C is equal to 1 over 2 pi FC. So what is the mystery of that? Well, 2, and pi, the 3.14, and then we can go 3.14159. I did note in the book he likes to use the 3.1416, which also is correct, right? Um, the F denotes the frequency of the signal being applied, and then C, of course, is the actual capacitance. So the measurable unit in farads, the actual capacitor rating. So what we would do is we would basically go through our formula, and we would really literally type this out, right? It would be 2 times pi times whatever frequency. Let's say, like, if we were looking at typical 60 hertz, right, in this case, and then the unit of capacitance that we have, and then inverting that, and that would give us our X of C, or reactive value of the capacitor. Now notice it is frequency dependent, so the signal that we have going through that, we would be basically making a statement as applied to that specific frequency. Now, if we vary the frequency, of course, that X of C rating will change. Everything else would be fixed, right? 2 pi and the capacitive rating, but the frequency, if it varies, then of course the X of C is going to vary with that. And here we see actual statements of what is going on when we do this. So if we look at it, like in this case, so he has a connected capacitor with a light bulb, and basically watching or observing the light bulb if it gets brighter or dimmer to see how current is actually flowing. So the current flows with AC voltage applied to a series connected. So it will go going through the capacitor and then through the light bulb. Um, So, and notice the statement here where there is no current through the capacitor's dielectric. Now remember, yeah, inside of this capacitor is a dielectric that is essentially non-conductive. So next statement here is, if we look at it, while the capacitor is being charged, by increasing applied voltage, the charging current flows in one direction in the conductors to the plate. So there's like an interesting phenomenon that occurs here. So essentially, what we're going to start looking at is what occurs to both voltage and current while the capacitor is charging. Okay. Now you notice with DC, it only does one thing. It merely charges up, and unless we provided some means for discharge, it would literally sit there at the charge potential and do nothing. Now, an interesting thing is with an AC signal, we have both positive and negative alternations. So the capacitor is allowed to charge up during the positive alternations, but it's allowed to discharge during the negative alternations. So the AC signal is actually charging and discharging through the capacitor. Now, this is something new for us, basically. And so we'll be observing this phenomenon of the charge and discharge and what exactly is happening. And I want you to think in your head, too, there's two things. There's both voltage and current that will be going through this thing, or trying to. So let's take a look at this next slide here. This actually helps quite a bit. So you notice that it's essentially a simple circuit, right? So we have an energy source here, 120 volts, 60 hertz, which is out of the wall power. We have a capacitor of 4 microfarads hooked up to a 15-watt light bulb. So basically what he's trying to show is how the size of the capacitor does affect what's going on. In this case, See, he has a 4 microfarad capacitor. The light bulb lights up very brightly. With a smaller capacitor in this middle diagram, he only has a 1 microfarad capacitor, and that gives off a dim light. And notice in DC, we get no light whatsoever. So basically, the capacitor in a DC circuit is stealing all the power. He has no way to discharge. I mean, he literally a charge up to that full potential, not unless we use like a switch of some sort to alternate or to simulate the discharge point for this thing. It's going to charge up to the full potential and block all the DC. It just says no, not getting through here, and we could prove it. Literally, there is no light that's involved in this. So this is a nice little diagram just to see, just show you. It's like, oh, what's going on here? Well, and like I saying, with the AC signal, you actually do have activity occurring, and with DC, nothing whatsoever. So this is kind of a new thing for us, and we'll be examining, of course, how this phenomenon occurs, and it's by the formula itself. By the formula, it's extremely frequency dependent as well. So the way this thing reacts, it's frequency dependent, because the capacitive value is fixed. Once you have that established, and then 2 and pi, literally the frequency is the only thing that you have that's a variable element within this. So if I were to apply 60 hertz in one case, I would have 1 X of C rating, okay, or 1 reactive rating. But if I applied something much higher, like 100 kilohertz or something like that, I would get an extremely different reading. So it is very frequency dependent. Excuse me. But in a case like this, with like he states in the very bottom statement, yeah, with a steady DC voltage source, right, it has 0 frequency. So even if we use that formula and we apply 0 to that bottom, then you end up with 0 in the denominator. And in math, there is no division by 0, because when you divide by 0, the statement comes out to infinity. So the answer could be anything. And that's what he means by this. With a steady DC voltage source, the capacitor's opposition is infinite. And that's exactly what it is. It's division by 0. Technically, that's a thing that's not allowed within mathematics, because infinity is not a definitive answer. It's like, because really division by 0 could be any answer at all. And like I say, it's infinity. It can go from like literally 0 to the highest number available, which there is none. Anyway, but yeah, so in the very bottom, it's like it says, it's in this case, the capacitor is effectively an open circuit. And it's true. Like in that case of the example, let's go back here, of this, you get no light bulb shining whatsoever. Then that literally is, and I mean, you have an energy source, right? Why is the light not shining? Well, this element is blocking all of that and treating it very much like an open circuit. You get no current through it. So here's a summary looking back at this very first section. Okay, what do we know now? That X of C depends on the frequency of the applied voltage and the amount of capacitance that is available. X of C, yeah, and it's because of this the fraction. You have 1 over the 2 pi FC, which means that any changes you make to either capacitance or frequency inversely affect the value. So if we raise the capacitance level, X of C actually goes less, and then it becomes less as well for higher frequencies. So basically, if we raise either the F or the C value of the fraction, our X of C will be going down. So in this case, we would have less reactance. So now we get into a little bit of math, and it's just playing with what occurs when we do these things. So if we look at the factors affecting X of C, okay? So in our statement, it's 1 over 2 pi FC. Well, 2 stays as 2. pi stays as pi. So the only two things we do have left that can vary will be the frequency and the capacitance. So in this case, he makes his statements where increasing C decreases excess C, and decreasing C increases excess C, it's inversely proportional. So because of that fraction, so as you raise or lower the value of C, you will affect the actual result. Okay, in an inverse relationship. So, and of course, usually when you increase something, everything else increases. But in this case, if we increase C, we decrease the amount of excess C. And the very same goes for the frequency as well, as you see in the bottom statement here. They're literally identical, right? Increasing F decreases excess C, and decreasing F increases excess C. So playing with either one of those values will affect the amount of excess C that we have available. So let's start thinking of excess C, because ideally that's when we use capacitors. We use them in an AC environment. And so we won't just be looking at capacitive nature, we'll be looking at reactive nature, how this thing reacts for that specific frequency. And there's actually things, as you'll see later on, that we can do with that. And some interesting things, actually. At least I think they're interesting. uh, so here's playing around with our little rule here, right? So we have a formula where x of c is equal to 1 over 2 pi fc. And I have a sheet I'll have printed out for you guys tomorrow, and it's got more on it than this, but this applies, so you'll be able to look at like what a specific circuit is with the formulas involved with that. Um, so if we make our statement, right, x of c is equal to 1 over 2 pi f of c, and juggling that around, okay, let's, finding our, if we have unknowns or something like that, in this case, how would I find c in this? Well, you merely do your little mathematical juggling here, and you find that, yeah, c is equal to 1 over 2 pi f x of c, as well as f. So all three of these will probably be formulas that you'll use like throughout the labs and throughout homeworks. So we will play with these. It's don't look at it as being very complicated. I mean, most calculators now have the pi value in there. I'm old school and been playing with it long enough where it's memorized. uh, so if we look at this, capacitive reaction is an opposition to ohms. So series or parallel reactances are combined in the same way as resistances, and they are. So if we do get an X of C value, let's say we have a purely capacitive circuit that we're applying an AC signal to. If we have the X of C value, we combine those and we treat them the same way as we do with resistance. Now, I know when we were doing the homework and we were doing the labs, like the Thursday lab, where capacitance, the way we did them in series parallel configurations was like the opposite of what we do with resistors typically. Now, remember, that's just for capacitive value. But now when we apply this AC signal, we sort of change things a little bit. So that's why when you say this, we're not saying capacitance, we're saying capacitive reactance. So once we get that X of C value, the X of C is equal to 1 over 2 pi F of C, we would have a value that would have an ohms rating to it. And so with that, we would be treating it the same way as like a parallel or series resistance and solving it that same way. So if it's all in series, the X of C's would just add up. And in parallel, we have to use our formula. Okay. So, but we'll be getting into that. That's kind of what tomorrow's lab will have. Simple circuits that we'll be applying signals to and looking at with the meters and the oscilloscopes and seeing how these signals are affected by the reactances. So anyway, so yeah, combining capacitive reactances is opposite to the way capacitances are combined, because reactance isn't in and of itself. Once we have the value for X of C, it's very much like the resistive value of ohms, but there are differences. Okay, so I don't want you to think that you'll be ideally treating them as the same as resistors, but solving them as far as the series parallel configurations will be very much the same. See, in this case, so if we want to, we have a series circuit with individual reactances, right? We want to find out, all right, so what's the X of C total in this case? And so you simply just add them up, right? X of C1, X of C2, so on and so on. And within a superior, God, that came out wrong. Within a series capacitive reactive circuit, all reactances will have the same current, right? Just like a series circuit does. So, and then of course, Ohm's law, the voltage across each reactance equals the current times the reactance, right? There's no variance there. So it's still E is equal to I times R, but in this case, it's X of C. If we have that, oh, hold on here. And then looking at the other side of the coin here, we look at parallel, and you can see it's done very much the same way as the resistors are, right? So we have to do the inverse, right? If we want to have X of C total, how do we solve that? And within this parallel network, just like in the resistors, all reactances will have the same voltage. So when solving, oops, going back here, right? So all in a series, all reactances have the same current, just like the rules that we've already established, right? And then the same with this, all reactances have the same voltage. So we treat them the same way as we do like with resistive elements with resistors. And again, plugging in Ohm's law, if we want to find out the current through this capacitive circuit, we would have the voltage divided by the reactance in this case. And here's a couple of diagrams now remember, this is just purely reactive. There's no resistor to this circuit. All we have is our energy source with one capacitor, and like in the very first case, and Ohm's law still very much applies. So you can see that for this capacitor, our X of C, okay, our reactive rating in this case is 100 ohms. So if we had 100 volts with 100 ohms, what's our current? It would be 1 amp. Same way with this, right? Because we would have the full 100 volts across this guy. And so then doing our division, 100 divided by 100 gives us the 1. Now we look over in the middle one, and we have two capacitors, okay, in a series setup. And so how was this set up? You see that X of C1 is 100 ohms, but X of C2 is 200 ohms. And so splitting it up, right, you can actually even see that now. So on the bottom one, we get the 66 and 2/3 volts. And then the top one is 33 and 1/3 volt. But, and then what our current is overall, and remember, this is a series, so 1/3 amps would be here and here. And then looking at a parallel configuration. Oh, my bad. Again, 100 volt source. But in this case, we have 100 ohm reactance in parallel with a 200 ohm reactance. And then solving that. Remember, in parallel configurations, current varies, whereas voltage is the same. And that's how we do the middle one here, right? Voltage is the same. I mean, current is the same. Oh my God, I'm so awake not today. But we treat it the same way. So what we learned before, as far as how we treated series and parallel configurations, very much applies here. I mean, our Ohm's law is still true, right? Kirchhoff's voltage law, Kirchhoff's current law, these still apply. And so now we're just basically adding to the things that we've learned before. And see, we're doing our building blocks here. And like I say, it very much does apply. So the only new thing that we're actually dealing with is the actual reactance itself, X of C. So some generalizations with this. So using X of C, the block direct current will provide low reactance for alternating current. So think about that. So in our like DC example, the capacitor sits there and literally blocks the DC, doesn't let it go through, the light never shines. So basically we have an open circuit, if you will. But it will allow alternating current to go through because of the positive negative alternation. So it can charge and discharge. So keep that in mind. That capacitors, they don't like DC. They shut it down. It purely blocks it, doesn't allow it through, and that's the end of that. Oh, and then and in this case, the cool thing is the resistors are purely that. They're like our stable point on all these circuits. Um, Resistors remain the same in DC or AC circuits. But we can see that capacitor does react very differently depending on the type of circuit, okay? DC circuit, it just shuts it down. AC circuit, well, it'll do a charge discharge thing. And that's what we're going to start looking at basically through the end of this chapter and definitely going into chapter 17, where we do start playing around with capacitors and how they react to different frequencies and what happens with that. Okay, and then a very bottom statement, another general one, right? The required C becomes smaller for higher frequencies. And this is true based on the inverse relationship of X of C. So as we increase that frequency, if we kept, well, you'll see that later on, what actually happens with that. And so we get a nice little table here. And these are very typical. And you can see for like power and low audio frequency that we have a fairly large capacitive value that would be used with this low frequency. So 27 microfarads is a pretty good sized capacitance. I mean, compared to like way down on the bottom here, if we look at like an FM radio with 100 megahertz, right? It's got a 16 picofarad capacitor to it. So there's quite a big difference with that. And as you can see, that the trend, if you will, that the higher the frequency goes, the smaller the capacitance. The lower the frequency, the higher the capacitance. And that's pretty much a rule. It's to keep it stable because at certain ones, I mean, based on doing that 1 over 2 pi f of C, if your value is so low, it's like your X of C becomes virtually non-existent. And I mean, what kind of circuit would you use? Because see how he says here, he wants a reactance value of 100 ohms. Because if you go too far down, then your reactance becomes, almost zero, in which case there's no point to that. So in this case, he says, okay, if we want to get a reactive value of 100 ohms, this is what we need to do to set it up. And so you'll notice, right, the higher the frequency goes up, the lower the capacitive value. And that's to keep that formula stable. So we get to keep a good reactive value, in this case, 100 ohms. And so here's a little summary, if you will. So what have we learned so far? That capacitance, what our symbol is, the unit is in farads, right? F. The value depends on the construction, as you've seen, that the parallel and the series networks and what happens there. And very typically, if we wanted like a high capacitance value, we like the parallel setups, right? And then if we wanted a low capacitive value, we would do a series setup. So, and then we look on the other side of the coin. Well, what do we see here for capacitive reactance? Well, our new symbol is X sub C. The unit that we use for this is ohms, right? And the value depends very much upon the values of C and F in that equation. And then that Ohm's law still applies and what X of C is equal to. Now notice the interesting thing in the bottom there that he states that, okay, X of C is equal to BC over IC or 1 over 2 pi FC. So both of those would work. And in fact, you could even use those together with like a substitution type thing to find, values of known and unknown throughout your circuit. Anyway, now here's a few other things to look at that'll get a little interesting. And we haven't dealt a whole lot with phase yet, but we'll start looking at that more and more and getting into what phase is and how that's dealt with in AC analysis. Because we're going to be getting an AC, we're going to have to start looking at the AC signal and dealing with the AC signal. And one of the things that we'll be looking at will be phase. We'll be looking at the time involved, the period, and how to analyze that AC signal slice by slice, if you will. Um, so if we look at capacitive reactance versus resistance here, okay, what are our symbols we use? In this case, for reactance, of course, we use X as C, and resistance, we use R. But the unit we use is still the same. We use the omega symbol for ohms. Um, what can we say here? That the value of this reactance decreases for higher frequencies. For resistance, the value doesn't change whatsoever. And an interesting phenomenon here, that current leads the voltage by 90 degrees. And in resistance, current and voltage are in phase. So when we do this, I want you to think of two things, okay? So when we have an AC signal going through, we have, now it's right in the name, alternating current, okay? So our current is fluctuating. We have a sinusoidal waveform coming through current. And with that, we also develop a sinusoidal waveform for voltage. So in effect, we have two sine waves. Now our oscilloscope, when we view it, we're looking at voltage. We're not looking at current. Now, we'll, hopefully in tomorrow's lab, we'll be able to show you a way that you can sort of look at current. Um, but when we look at that, that's what we're viewing. And so what happens with the capacitance is a blocker. It likes to hold things up. Well, in this case, we're going to make a unique thing happen that we're going to be taking a look at here, where we have, okay, sine wave charge and discharge, and what exactly happening when we do this. So if you look at this simple circuit where we have the energy source, right, in this case, it's an AC signal with one single capacitor and our full potential here going across. So on the one alternation, okay, in this case, let's see, we have the negative alternation going on. So one time it increase, it'll start charging the capacitor, and then in the next alternation, it discharges, charging the capacitor and discharging, charging and discharging. Um, so what happens is basically the signal comes through and the capacitor is grabbing it and charging up with it. So there's a time effect being held here. So he stops the voltage, but then in the next alternation, when we swing negative, he's going to release it. So what he's doing is not really stopping the voltage, if you will, but merely holding it up for a time. Now, current in this case is still allowed to flow through without opposition. So our current sine wave is going in just as it came in, right? Nice and easy. But the voltage, it's being held up a little bit. So what happens is the current flows through, but then the voltage starts to, the sine wave that happens there starts to lag, and it gets out of sync with the original signal, very typically in this case by 90 degrees. And we have a shift. And so essentially what you end up doing is the one wave would be a sine wave, and then what we have now created is a cosine wave that is still running with this. I mean, there hasn't been any holdup, right? The capacitor is still allowing it through. It's just merely stopping it for a time. Now he takes a look at, and now when we look at this signal, okay, and we're not gonna, it's because we have little derivatives going on here. Basically, he's just doing it as a demonstration to show how, and again, this is Ohm's law, if you will, in a sort of sense. So what he's showing is the dV dt. What that is voltage with respect to time. And so, because you have to think of our signal is constantly changing, or in a state of flux, if you will. It's never at the same point. If we can pick a period in time, it would be this, and then this, and then this. But it's in a, it's constantly changing. So unlike DC, we don't have that nice fixed value where we could say at any moment in time it's this. No, in AC, at any moment in time is something we have to actually examine because it's in, it constantly changes. So that's what he means by that, volts per second. So with the respect to time, we could find out what it is at that particular time with respect to that particular signal. And so we're not actually going to be using this formula per se, but it is a way to express what is actually occurring with the capacitor. So here's our phenomenon. That's 90-degree phase angle. Okay, IC is going to lead BC by 90 degrees, and that is caused by the reactive effect of the capacitor. It's literally charged up, so that voltage signal when it's coming through is being held up, charged up, and then let go, whereas the current is allowed to let go unaffected. And so, yeah, what happens is we end up making a phase shift of the voltage signal, which puts it out of sync with the original signal. And again, it depends on the rate of the voltage with respect to time and not the voltage itself. It's actually just the changes that occur over time because you're going to have different amplitudes at different moments and that type of thing. All right. And then very bottom statement, a ratio of BC over IC specifies the capacitive reactance in ohms. So remember that reactance is always measured in ohms. There is no difference as far as that goes. It's just where it is. So here's what it would look like if we could measure both simultaneously, if you will. The let's say here, like the red one here and the blue one. Okay, and how much shift that we have occur. And this is very much what it would look like. And you can see that we use the cosine symbol, okay, to show our shift of that 90 degrees. Because normally what we'd use is like the V instantaneous voltage, okay, like trying to find the voltage at any particular moment in time would have been V max with the cosine, with the sine of theta. In this case now it's changed. We're not using the sine of theta any longer. Now we're using the cosine of theta because of that shift. Oh, and this rule very much applies because what it allows us to do, that Vmax, that could be like if I picked a given port, on the sine wave and said, okay, my amplitude is here. And so what you would find out then, it's like, well, if your amplitude is there, then that's at a specific angle and a specific amplitude. And so we would have to find what that is. So the thing with this, it's never the same. It's never the same, over time because this thing is in a constant state of flux. And so that's why we look at it like we do with that. And so given there are specific angles involved and crossovers, and we will be taking a look at that. More so in the next chapter. So right now, so with this chapter, and this is pretty much the end of the chapter, by the way, guys. So this is like basically introducing the new concept. So I hopefully, like with tomorrow's lab, we'll be taking a look at that. Not too math intensive yet or anything like that. What we want to do is observe the phenomenon that occurs. So hopefully with tomorrow's lab, and I do throw a resistor in there. That's why this one lab could last for the whole week, depending on how well we do tomorrow with it and, grasping this concept. I know it's new. It's new. Don't be scared of it though. All we're doing is observing a phenomenon that occurs, right? And it's an interesting thing with capacitors and how we deal with them. And then what we'll start looking at in this case, in the next chapter, 17, we'll start actually seeing what we can do with that and playing around with it. And what we'll do is we'll add a resistor element into it. So what we'll have is RC circuits. So it'd be resistor and capacitors together. And that's where it gets interesting. Because then it's not purely resistive, it's not purely capacitive, but a combination of both. Because if it was purely resistive with the AC signal, well, that's easy, right? We're no brainer. We just follow through and it's like, well, this is what this is and this is this. And capacitors, our biggest thing is the phase shift, if you will, from the voltage current. Now they have a phrase for that, but we haven't gotten into inductors yet. But they called it Eli the Iceman, and I could draw it out for you tomorrow. But ice applies for capacitance, and what it is the C in the middle of ice is supposed to be okay. That's my. It's like a little memory thing, where C is the capacitance, and what it means is the I leads the E, and then the other way around. Well, anyway, but yeah, but when you think of capacitors, think ice, right? The current is going to end up leading the voltage. And if it's purely capacitive, then it's going to do it by 90 degrees. And it'll shift. It'll literally turn that sine wave into a cosine wave. And that's all that is, man. I mean, something like that with that bottom formula, we would use that to find what our instantaneous voltage is at a given, amplitude and phase, if you will. Because think in your head here, it's like, okay, when we start these things at the 0 point, that is the 0 degree point, okay? And then as it goes out, peak amplitude is 90, and then it's 180, 270, and 360 for a full cycle of the signal, okay? So then when we have this start to happen here, well, now we're out of phase with this and it shifts everything. But our angles still apply. So we just have to re-affect that, right? So with the red signal, I would be using a similar formula as this one, but instead of cosine, it would be sine, because as a sine wave, we start at the 0 point. But if your signal starts at a different point, other than that, it's no longer a sine wave, if you will. In this case, that 90-degree shift with the blue signal, it's a cosine wave. Okay, and I don't want to get too deep into trigonometry. Like I say, I am not a math teacher. I am an electronics teacher. So but I'm going to go ahead and assign this homework up. Now, here's the thing. I'm done with this, by the way. Unless you guys, anybody have any questions on that chapter? I know it's just, I mean, we'll go through it. It's going to be kind of our focus this week. We're going to be looking at that. I mean, the first two, and it's like, you got to have your building blocks, but as you've seen, capacitance by itself is pretty damn boring. With DC, it's when we apply AC that it gets a little exciting, and I know it gets a little mathematical too, but unfortunately we have to do that. We do have formulas and we got to do a little math, but it's an interesting phenomenon to see how this occurs. But like I say, we'll be keeping this more capacitive in the beginning. I do have a little thing with tomorrow's lab where I do have a resistor in there, but that's really to help us more observe signals, if you will. But if it take, we can make the lab be all week just because of I do have an RC circuit at the very end. So we'll see how we do, and then we'll go from there. And the same with the homeworks. If this is too much and everything, you guys got to let me know. I mean, really, I'm pretty open. I'm not like, everything here is not set in stone. If we need to vary some stuff, you need more time on something, let me know. It's not a big deal. We get through it. As long as we get through our work and get through our concepts here that we need to get through by the end, then we're pretty good to go. But I'll for today, we're gonna have chapter 15 homework will be due, I don't know, I have to relook at that. Let's say, I think it's by tonight. And I did assign the quiz. So chapter 14, 15 quiz is out there. And that I gave us 24 hours, I think. It's due by 9 o'clock tomorrow. So if you get to, basically you have the whole rest of the day and all night and in the morning. But yeah, there is a quiz out there. The chapter 15 homework. I'm going to probably throw chapter 16's either on there tonight or tomorrow. Oh, my wife is home. She works nights. And I have dogs. Oh my goodness. I have big dogs too. No, good. And that's my wife. She doesn't always yell like that, but sometimes. Anyway. But no. You guys have any questions on any of this so far, or we're pretty good to go?
I'm pretty good.
I'm good.
Well, tomorrow I'll hand out that lab, and I'll go over some of the, we'll go over some of the stuff again tomorrow. I'll bring in some. I got some worksheets and stuff, and and definitely I got this formula sheet for. It's for both. It's pretty much for everything, but this will apply for this part of it because it does have the formulas for X of C on it and stuff. But don't get intimidated by it yet. It's like, oh my God, we haven't even done this crap yet, and it's like, no. But this sheet's like it's like the formula sheet for the rest of pretty much the whole rest of the 7 weeks we have left together here. But anyway, but yeah, that's pretty much it today, guys. I'll post this, the lecture on there, but I got the quiz out there. If we need more time, like I like in the chapter 15 homework, let me know. I can extend. I'm good with that, but I am going to post chapter 16 as well. I'm not going to go, I know in the beginning there, I know I did the full 50 questions for both of those. I'm not going to do that with these next two chapters, just because there's more to it. I just wanted to make sure that we did get those ground concepts down pretty good and everything in the beginning there, because that's just important to, really get these concepts in there. I don't know. But so yeah, we'll go over this tomorrow. We'll have a new lab, and we'll see how that goes, whether it's going to be just tomorrow's lab or the lab for the whole week if we need to, as long as we get through it and get our learning in there, and then yeah, basically really get through the quiz sometime, today, or like I say, up till 9 o'clock tomorrow, I think is the due time. Okay. And other than that, that's about what we have for today, gentlemen. All right.
Sounds good.
All right. Yep. And I will see you guys tomorrow.
See ya.
See you, Tom.
Um,
Bye.
Bye.